Hello everybody, Professor Dustin here. In this video, I'm going to give a brief introduction to the spring force, which is also known as Hooke's law, and also I'm going to do an example so you can see how the spring force works in a specific case. So the spring force is a pretty simple idea. It's the force that the spring responds with when you push on it. So it's how much force you have to push on a spring and how much force the spring responds with when you do push on it. So let me draw a picture of the spring and then detail what the spring force looks like. So here's a picture of a horizontal spring. There's some kind of wall on this side, and I'm going to label this as the x direction. Right now the spring is uncompressed, and so I'm going to indicate that there is some x naught. That's the so this is the x-axis, and x naught is the uncompressed position of the end of the spring. And then what I'm going to do is I'm going to redraw this picture and compress the spring towards the origin of the x-axis. So you can see what I've tried to indicate there is that I have compressed the spring a distance x from the original uncompressed position of the spring. And the question is, well, there's two questions, right? One is, how hard do I have to push? How much force do I have to apply to do that to the spring? And then how much force does the spring apply to my hand as I'm doing that? And so both of the things that's a Newton's third law question, right? So they're obviously equal and opposite forces, those two forces. So typically what we do is we just talk about the force that the spring responds with. So how much force the spring is applying in that direction. We call it the spring force, sometimes FSP. There's a number of different ways of writing the spring force. The typical way that I like to do it is minus K x minus x naught. So notice that x minus x naught, that's like a delta x. So you can also write the spring force as minus k times delta x. So let's try to identify what all the terms in this equation actually are. Recall that k, we call that the spring constant. Constant because once you know it, you know what to plug into k. It doesn't change, but for every spring, there's a different spring constant. So this is unlike the constant due to gravity, big G or even little g, in which once you're on the Earth, you know that little g is going to be 9.81. That this is different. You need to know specifically which k applies to your spring, what the value of k is for your particular spring. We should also look carefully at what this x minus x naught means. So if I've picked x naught to be where I've indicated, and then I've picked x to be at a position down here, that means that my current x position is less than x naught, right? Because if my x is 0 here, getting positive in this direction, x is less than x naught, and that means that actually x minus x naught is negative, is less than 0. What does that imply about this equation? This means, because there's an extra negative sign here, that the spring force is positive in this example. And of course, that's what you want. If when I push in the negative direction on the spring, you want the spring to respond in the positive direction. That's what I've indicated by this arrow here. So that's how you explain all those various negative signs. One thing that's very common in spring problems is we often take x naught to be simply equal to 0. And in that case, the spring force looks a lot simpler. It's just minus k times x, where if you push towards the negative direction, x gets negative and this whole thing becomes positive. Whereas if you pull the spring in the positive direction, then the negative direction says the spring responds in the other direction. So this is sometimes a more sort of conceptually easy way to understand the spring force. Notice that I'm not using any vectors here. Forces are vectors, but typically when we talk about the spring force at this level, we don't talk about it as a vector. This negative sign sort of takes care of the directionality, and we only ever use the spring force to be directed in one direction. Now, we don't have to do that. We can obviously write down the components of the spring force, but that typically leads to more complicated issues that we don't generally want to cover at this level. Okay, so that's a brief introduction to the spring force. Now I'd like to do an example of the spring force so you can see how it's used. So in this example, I'm going to start with a spring that has an unknown spring force. So I don't know what the spring force is. So the first question we want to answer is find the spring constant. Okay, so that's actually a pretty simple question to answer. What you do if you want to find the spring constant of an unknown spring is you put a block on top of the spring, or you put some amount of mass on top of the spring. Let's call that mass M. And let's give it some specific values. Let's say we put a mass of 5 kilograms on top of that spring, and we can measure that the spring compresses a distance, let's call it d, of 10 centimeters. So what we can do is we can use Newton's laws to determine how big the spring constant K has to be to make sure that that mass is balanced against the force of the spring. So let's first get a free body diagram on this mass. So there's a force going downwards, that's the gravitational force of the Earth acting on the mass, and there's a force going upwards, that's the force of the spring is applying. So if we try to solve Newton's second law in the y direction, we'll get that the sum of the forces is equal to 0. They're equal to 0 because this mass is not accelerating, it is not moving at all. So then we can put in the two forces in this problem, the spring force minus the gravitational force should be equal to 0. And now we can put in the definition of the spring force that we learned in the last slide, minus K times x minus x naught minus mg equals 0. And so now we need to deal with the x minus x naught piece of this, which means that we need to set x naught. We need to determine at what x position the spring is uncompressed. So for me, I think it's going to be easiest to just pick x naught to be right here and pick it to be 0. So I'm going to pick the origin of my coordinate system to be right there. That means I'm measuring x upwards, like that. And so that means x naught is 0. And then this x value, well, this x value actually has to be negative, right? Because I'm compressing the spring in a negative direction, a distance d. So I'm going to put minus d into there because it's downwards with a value of d. So collecting all those things, I can now write this as minus k times minus d minus mg equals 0. I'm going to rearrange this by moving mg to the other side, and I'm going to kill the negative sign on the left-hand side because minus k times minus d is just d times k is equal to mg, and now I can divide by d to figure out what the spring constant k is. It is mg divided by d. If I plug that into my calculator, I can get a value of 491 Newton per meter. Notice you have to be careful with this value because you have to convert the distance d into meters because it's given in centimeters. And actually this is a pretty reasonable spring constant. Just remember about spring constants, they can be quite large even in sort of normal everyday situations like in this problem. Okay, great. So now I've found the spring constant for this spring. I'd like to do one more example and balance this spring, this mass and this spring against a few other forces so you can see how it works in general. But I'm going to use the same spring constant that I determined here and this same mass in a slightly different statics problem. So what I'd like to do here is I'd like to take this block. I'd like to suspend it in midair with a string that goes up here. I'm going to call the tension on that spring Ft, that string, sorry. And then I'm also going to have the spring on that side of the block, and this is like attached to a ceiling, and this is like attached to the wall. This is the same block I had before, so it has a mass of 5 kilograms. This is the same spring I had before, so it has a spring constant of 491 Newton per meter. I'm going to say that the angle that this rope is acting at is theta, and let's give it a specific value of 45 degrees. And so I want to find out two things about this problem. I want to find out what Ft is, what the tension in the string is, and I want to find out how far the spring is stretched. Of course, we can kind of assume that the spring is being stretched and not compressed because the direction of the tension force is away from the spring. So I think we can assume that the spring is indeed going to be stretched and not compressed. Okay, so how are we going to solve this problem? Clearly this is a Newton's law problem because we have a bunch of forces keeping this block in equilibrium. So we certainly know that we're going to have the sum of forces in the x direction be 0 and the sum of the forces in the y direction be 0. That's just the condition of the block being static. And let me put the x and y directions on here explicitly. And actually, let me draw a free body diagram of the picture down here just so we can be clear what is happening here. So we have a gravitational force downwards. We have a tension force directed upwards at an angle of 45 degrees. And we have a spring force, which we believe is going to be going in the negative x direction. Okay, so let's start filling out our Newton's second law here. Let's do the x direction first. So the sum of the forces in the x direction, we are going to have the tension force times cosine 45. That's because, of course, we want that component. Ftx is going to be Ft cosine theta. And then we want the spring force. So that we have to be very, very careful with the spring force, with the sign of the spring force. I'm going to write this as minus k times delta x. So I'm going to leave delta x as like unspecified sign. Now I expect delta x here is going to be positive because I've put the negative sign in there to indicate it's going backwards already. But I'm not going to make any guesses about it because I feel that might be a little bit dangerous and I might screw myself up. Those are the two forces in the x direction, so they sum to be 0. In the y direction, I can sum up the forces, and I'm going to get the other component of Ft, that's Ft sine theta, and of course that's the component right there. Fty is Ft sine theta, and then I've got Fg going downwards, that's going to be minus mg. Okay, so you can see that we now have two Newton's laws equations, and so what are the two things we're trying to find? The tension force, which is right here, and the distance the spring is stretched, which is right here. So two equations, two unknowns. This is certainly solvable. In this case, we can do even better because this equation, the y direction, doesn't have the spring force in it whatsoever. So we can immediately solve this for Ft. And that's going to give us Ft is mg over sine theta, which I can plug into a calculator to get us a force of 69.4 newtons. And then I can go back to the x direction and solve for the displacement of the spring. Sorry, this is getting a little bit crowded. I can rearrange that to write delta x is Ft cosine theta over k. Now, I've been careful with the negative signs by putting this guy on this side, making the whole thing positive, and then dividing by k. And actually, I'm going to do something just to make this a little bit more accurate. Instead of putting in the number Ft into there, I'm going to put the equation Ft into there. That will ensure that I don't have any rounding issues. So if I put Ft into there, I'll get mg over sine theta times cosine theta over k. Now I have the nice trig relationship right here. Cosine over sine is going to be a cotangent. And my final equation is going to be mg over k times the cotangent of theta. And so now I can just plug that into my calculator. Okay, so if I do that, this is kind of funny. I get delta x is equal to 0.10 meters, or very close to that. I get 0.99, 0.09999. So this is actually about the same amount the spring was stretched in the original problem when I figured out what k was. That's just a coincidence. If I had changed that angle to be something different, I'm sure this 0.1 would have been some other value. So that's just a coincidence. Anyway, sorry about all the clutter. I just wanted to get this video out there as quickly as possible. This has just been a little introduction to spring forces and then 2 quick examples of how to use spring forces so you can see some of the details around them. They're not too tricky, but basically everything comes down to making sure you know what's going on with this sign in front of the spring force. And that's just a matter of checking your work at every step to make sure that the force is pointing in the direction that you expect it to be. Okay, great. Thank you guys for watching, and I will see you next time.